brief introduction, who's PROTOS and why do we think we can talk about such things? We develop tools, test tools, software architectures, tool chains, domain-specific languages, and so on for embedded systems. So we are specialized to improve the development of embedded systems by providing tools and methods. Who am I? I'm Thomas Schütz. I'm CEO of PROTOS, and I'm an aerospace engineer with a fable for embedded software architecture, tests, and tools. So today we're talking about architecture for embedded systems. Yeah, everybody does a little bit of architecture, a couple of diagrams, maybe some layers, and so on. The problem is the architecture is not very often put into the center of the development because yeah, you create a couple of diagrams, for example, then you start to program in C or C++ or any other language, and soon the architecture is forgotten and you focus on the implementation and you decouple completely from your original architecture considerations. So why do we place now the architecture into the center of the development? The only thing we have to solve is complexity. If it's not complex, it's not a problem. So if you have a safety problem that is not complex, it's not a problem. If you have a big red button that takes away the current and the air for a machine control, for example, that's trivial to do. It's easy to test, so it's not a real problem. But if you want to shut down a car which is going with 200 kilometers an hour on a German Autobahn, you cannot just stop because there's inertia. It's a dynamic system, so you cannot just say, okay, let's hit the brake and take the hands off the steering wheel, because it's a dynamic, very complex dynamic system. So the safety is complex because it's dynamic, and that's something you need to consider in the architecture before you even start to develop. So you need to consider the complexity. The biggest thing you can do, the biggest leverage you have is abstraction. I'll give you a little example from real world. If you count, for example, those matches, usually most people say, okay, it's 30, 50 matches, maybe 100, but nobody's really sure whether you're even in the right range. So if we rearrange those matches, it's the same number of matches. Feel free to count them both, but immediately you can see it's a 123 matches. So what happened here? The right picture is an abstraction in comparison to the left picture. Abstraction is always you leave something away in order to get a clear picture of a certain aspect of your system. It's never your complete system, but it's a certain aspect of your system. For example, in this case, it's the aspect you want to count the matches. That's the only reason for this pattern. So what did I leave away? You always leave something away with abstraction. I left away the position in space. So I reduced the position in space to a certain pattern, by that improving the countability. So that's just a little example of a real world example. But your real world software systems look more like that. And to prove this to you, that's a generated class diagram of a motor control system. It's a medium-sized motor control system, not even very, very complex, but a flat class diagram with all the classes and the relations. All the lines you see are the relations between classes or between C modules, for example. This does not help at all, because a UML class diagram is not an abstraction. It's a graphical view. It's valuable because of that. But if you do not reduce it, if you do not leave things away, it doesn't help you to understand your system. And that's a real world system here. So that's the power of abstraction. So how does this help in software development? Let's have a look at something we call abstraction and automation with model-driven development, including tests. So in the end, what you want to achieve, you need an executable that runs on your microcontroller, on your processor. That's a hex code for an STM32 ARM processor. There are a lot of details in there that explain the processor completely, what it has to do, step by step, every little single assembler or a machine command. So that's something we cannot understand as human beings. So we have high-level programming languages like C. In C, you explain step by step to the processor what it should do. So it's the logic behind your program execution. So you have control flow, you have, in this case, switch case statement, and so on. And we have if you have a closer look at this program, there's a switch case statement here with a trigger for a timeout and a state and so on. It looks a little bit like a state machine, but it's still a lot. There's still a lot of technical details to really implement the program. What we really want and need to discuss functionality. So what does my system do? This can be done much better on a higher level of abstraction. I leave away the implementation details. I don't care about what the implementation for a state machine looks like. If I want to discuss functionality with my customer or with the system specialist or requirements and so on. So that's a state machine. And of course, to implement the state machine, I need something like a piece of C code or so. And from a C code, I can derive the executable. So what happens here is we go from the C code, we have an abstraction from the executable, we have an abstraction to the C program. It's already better to understand for a human being, and another abstraction from the C program to the model. So that's the abstraction. And now, if you want to work on this high-level abstraction like a state machine, you need, of course, to generate C code or to interpret code, whatever the measure is. And then we need to compile the C code into an executable, and that's the automation. So on a C program level, you explain how you do it. On a model level, like a state machine with high-level abstractions, you explain what the program should do, not how it should do it. So there are many different ways to implement a state machine. I'm not interested in that. I'm interested in the functionality. So that's abstraction and automation with model-driven development. Let me introduce you to the method ROOM now, real-time object-oriented modeling. With this method, it's from the domain of telecommunication and machine controls, also airplane development and so on. So highly complex distributed real-time systems. And it's a method that puts the abstraction, the architecture model into the center of the development. So it's an architecture model for structure and for behavior. And it's formal enough so that you can generate code. So you always start with the architecture. You design hierarchically structured behavior. You make layers. You make containment hierarchies, the interaction between the components, sequence diagrams, state machines, and so on. And from there, you can directly generate executable code. So you generate the application. Of course, you can add manual code, for example, a protocol you already have, or drivers, or whatever it is. But you can always encapsulate into those components, and by that reuse those components in different contexts, and also test them very good. So now on the right leg of the V model, you need to test those components or those models you design. So you can, in the same method, design and run the software in the loop tests. For example, one component with the implementation, one component with the test case, and one tests the other. And you can use the same method also for hardware in the loop tests. If you just replace the interface between software elements by interfaces to a hardware in the loop test system, for example. it's everything in the same method. And in the end, you want to automate everything with continuous integration. So building and delivering your software, testing your software on all the levels, SIL level, software in the loop level, hardware in the loop level, component level, whatever it is, you can automate it with this method very good. So the method is called real-time object-oriented modeling. We made a new edition of this book. Thanks to the authors and the Wiley publisher, we could republish this book anew. So it's available online, of course, and at Amazon and so on. And the method has been designed for complex embedded system, and it's a real methodology, including modeling language, but also a process. So it's much more precise, for example, than UML. UML is good for documentation, for communication between people, but it's not very good to generate code. It's just not formal enough. So this method puts the architecture into the center of development, and it enables to integrate many other tools and methods by integrating them into those components. It has a very clearly defined semantics to enable code generation, and it's really good for concurrent asynchronous real-time systems. So most real-time systems are concurrent, asynchronous, even distributed, and so on. That's what it's been made for. So we implemented an open source tool chain. It's called eTrice. It's an official Eclipse project. It's a bigger Eclipse project, and we are driving this project since 15 years or so. So it's well established. And eTrice, you can see the link here, eclipse.org/eTrice. Of course, it's a new language. It's a new method. So if you run into any problems or any questions, don't hesitate to contact us or me directly, and we can discuss your use cases, no problem at all. We support you, of course. And so let's have a look at the process. It's just one possibility to run this process, but that's the main process we use. So you start to specify scenarios with sequence diagrams. That's one point where you can start. So you define the interaction between components. For example, a use case, you press a button and then the traffic light goes to green or whatever it is. So then the next step is you design the structure and the interface between the structural elements in your software. So interfaces are always designed with ports. Then you define a behavior. So every component can have a behavior. It can be a state machine, a model state machine. It can be also manual C code if you want, or anything from any other method that generates C code, for example, or code in general. You can integrate this very good here. And then you generate the C code, or you generate the code. It's not only C code, it's code. You compile it, you let it run on the target or even on your Windows PC, on your development laptop, or wherever it is. Doesn't matter because it's always portable. And then you debug and learn by having a look at the during runtime generated sequence diagrams, for example, where you can see what your system actually did. So on the left side, the specification, on the right side, what did your system really do during runtime? So and then you iterate, of course. It's a very fast and very precise process, and you start with a little architecture and you refine your architecture further and further. So basically you make a lot of architecture iterations. And if you have an implementation problem because your architecture is not good, you go back to the architecture because it's the same model. So you can rearrange the architecture much easier than with a piece of C code or so. Let's have a look at the main components or the main elements of this language. In the main building blocks of a room model are the so-called actors. They define the structure of a system, and they only communicate via ports or services, which are also ports. And so the ports are the only way to communicate. And the port also defines a specific role of the actor in its environment. By that, you have a very strong decoupling of the components, and you have a very strong separation of concerns if you use the method right, of course. Yeah? And we chose to implement the complete language as a textual language with graphical editors on top of it and graphical viewers. So for example, you can edit those components in a graphical editor or in a textual editor, but we always store we persist the models always as a textual syntax, because then you can diff, merge, reuse it more or less like a piece of Java code or so. Still, you have those high level abstractions and you can use the graphical editors. That's a very powerful thing, because with most modeling languages, you cannot really diff or merge or branch models very good. And that's completely solved here because we use textual modeling languages here. The same with the state machine. So every component can have a state machine or manual code, but state machine is the preferred implementation for those systems for the behavior. And hierarchical state machines define the dynamical behavior. Again, you have hierarchical state machines here, and you can see here the same state machine in the graphical editor and in the textual editor. Again, it's only stored in the textual editor, because then you don't have this diff and merge problem. So you can really work concurrent with the same model. So how does this help? Now I introduced the method, but we have a lot of elements in this method. We have actors, we have containment layering. So basically, it's a really good good balanced number of methods that work together closely to enable the definition of an architecture and executable code as well. So those are the Room features. So there are some more features, but those are the basic features of Room. Now, in order to design good architecture, I always have a look at the principles of architecture. Software architecture. So there's abstraction, separation of concerns, simplicity, encapsulation, modularity, and conceptual integrity. So for example, why this helps for modularity is pretty clear, because you have component with ports that are really good decoupled from each other, so you can reuse and so on. So, but in the end, what I really want to, what I really need are non-functional requirements. The functional requirements are usually the simpler ones to fulfill, but something like safety, security, robustness, scalability, testability, maintainability, lifetime life cycles, and so on. Those are the really hard ones, and they drive the complexity. So, for example, if you have a non-safety critical system and suddenly it becomes safety critical, you need to add a lot more considerations into architecture and development and testing than before. You just need to do this. So it makes it much more complex. So let's have a look at, for example, the non-functional requirement testability. I want to test something. So which principles do help by implementing a testable architecture? That's mainly separation of concerns. If I play divide and conquer, I can much better test single aspects, single concerns than if I mix all together. Then of course encapsulation, and because encapsulation is very important for black box testing, that's not so complex. And of course modularity, because modularity with a strong decoupling and cohesion for those modules, you always have the minimal interface to run your test case. And also modularity helps with reuse, and to test something is just another form of reuse. So you take a component and let it run in a test case. That's a reuse of your component. That's very important. And that's why it's so hard to test, because things are not decoupled very often. So because there is no architecture driving things into the right direction here. So now those principles help me, but how does Room help? Let's have a look at, for example, modularity. You have a very strong aspect of modularity in your actors with the containment hierarchies to give you the cohesion, decoupling and cohesion. And the actors with their ports have a very strong decoupling from each other. So every component only talks to its own port, to its own interface, and does not know anything about the other port on the other side. That happens one layer above. So I can rearrange my components with ports however I want as soon as I satisfy the interfaces. So there are no hidden links or something like that that would make the, so for example, global variables or something like that. That's just not possible with Room. Okay, so that's how Room helps with the architecture principles and the non-functional requirements. I'll give you an example from a machine control we did ages ago. And when the developer, the mechanical engineer, started to develop the machine, he drew a concept for initial concept on a piece of paper, and that's the original paper here of little part of this machine. This machine has a couple of hundred I/O points, digital, analog, motors, cylinders, and so on and so on. And in this case, that's by the way, those are inhalers for asthma for your lung at Paritech. And here you see a module that is running on a conveyor belt. Is stopped here, and then here are the filters for the valves for the inhaler. Will be pressed upon the inhaler here. So there are a lot of cylinders. Those are all cylinders, pneumatic cylinders, electric cylinders, sensors, and so on. So that's very typical for a machine control in a production plant, for example. And what we did is we derived from the mechanical structure, we derived the software control structure. So for example, for every cylinder, we make an instance of a cylinder that's able to control this. And we just drag this together because we already have the component cylinder. And something more complex, like here, this Deckelzuführung, so the tabs that come here, they are more complex. So we create subcomponents for that. And we hide the functionality away, because the only thing I'm interested in, is there a new tab or not? So that's the only thing I need to know. So everything else is hidden from sight here. So on every level, those control systems look as simple as you can see it here. And then, but that's not enough. Now I have to define a behavior for this machine control. So for example, that's a little state machine, in a sub-state machine actually, that controls the moving out or grabbing a tab, moving in, placing it on top of the inhaler, and so on. So that's the state machine that just tells the cylinders, now you, now you, now you, in, out, and that's it. So really, really low complexity here for an overall very complex machine. So just as an example, so in this case, for example, about 80% of all IOs are controlled by one class, the cylinder. So in this case, we have about 95, 98% code generation. For other systems, you might have 50% or 80% or 70% or 30%. The important thing is that you generate the architecture. Whether the implementation is manual or not is not so important, because you encapsulate. So what else do we do with Room? Room allows the integration with other tools and methods, because you can encapsulate them into those actors. So what are the use cases? You can develop distributed real-time systems, software in the loop tests, hardware in the loop tests, integration and system tests, environment simulations, system simulations, and so on. So you have a wide variety of things you can do. In the center, we always have the actor with its different ports. for different roles, for example, a functionality, a control, a configuration, and the lifecycle port. By that, we get a really good separation of concerns and a really high reuse of components and interfaces. And we can integrate into the actor different behavior languages like state machines, which are part of Room. With our PROTOS data flow language, you can integrate generated Simulink code, for example. You can integrate high-level programming languages. So you can decide what you want to, how you want to implement something inside here. Another important thing is, since we have formal description of interfaces, we can easily generate interfaces and the functionality like bus protocols. So for example, we have bus protocols generators for CAN, LIN, XCP, and others. So if there's any format we can parse in and generate a protocol out of it, it's really easy to do. And you always end up with an actor that can speak CAN or can speak LIN or whatever it is. And then you can integrate it easily into your application. Same with low-level I/O, digital, analog, all those low-level bus systems, protocols, Modbus, EtherCAT, TCP/IP, and so on. So it's always the same method basically to integrate external code or external tools. And the last thing you need to integrate with test and verification languages. For example, we have a test description language and code generators for the language Cage, which deeply integrates with Room models. And we also can integrate interface contracts for model and runtime verification. So while you're modeling, you can already verify whether the model is correct with respect to the contract you designed. That's a very constructive way to create safety critical system, robust systems. So you construct it in a safe way. So now let's go to a little demo. I prepared a little demo for you. I'm going to switch to my development environment. So here I brought you a little Room model. Let's make sure that it, yeah. So now in this, that's the application here. So everything that's inside here will be generated in C code in this case, compiled, and you can run it immediately. So double click, and now I need an interface. I need a traffic light controller. I will create a little state machine. I'm switching in the same component to the textual syntax. Now I'm in the traffic light controller, and I prepared a little empty traffic light controller here. That's really empty. It's an empty class. And so I go back to my graphical interface and integrate here the traffic light controller. Let's name this controller. Okay, so now I have a traffic light controller. Then I want to integrate, I need the interface because I have a little traffic light here. That's a Java user interface that listens on a TCP/IP port for one local host. And now I prepared a little component. It's called traffic light interface, TL interface. Let's call this way. So, and this traffic light interface contains a little state machine, easy to do. So, for example, if I set the car red, it sends over the TCP/IP port the set car light red, true or false. So it's a really simple state machine here. And of course, here now I need a payload as a TCP/IP. I need a TCP/IP client. So let's call this socket. That's a ready-to-use component that's in the library of the open source project. Over the control port, I configure the TCP/IP port, and over the payload port, I send and receive the payload. So why do I have two ports and not one? Because in another system, I might use a UART instead of a TCP/IP client. So if I separate those interfaces, I can easily use the same payload protocol here for UART, for SPI, for whatever you want. You just need to change the control port with a different configuration. So even the traffic light interface could be the same then. So now the last thing I need is I need to implement the controller. So I'm going to make a little implementation. So let's call this TL for traffic light. And we have a traffic light interface. That's the protocol now. So the interface definition, now have a traffic light interface. I can connect this here. And now I already have a system that can be generated, compiled, and run. It doesn't do anything, of course, so because I don't have a behavior. So let's start with the behavior. I'm going to start to connect the TCP/IP interface. Okay, so I say traffic light.connect 4441. That's the TCP/IP interface. And when it's connected, I set, for example, the traffic light interface set car green to true. That's my initial state, and the set car pedestrian red to true. So this would be the initial state. Here you see all the interfaces you have in the model. You can directly select them and use them. So now I messed it up. TL dot set car green true, and TL set car ped red to true. Okay, so and now this transition I take when traffic light is connected. You can see you can also wait for the request button, so the pedestrian that hits the button, for example, and so on and so on. So that's how you develop the state machines. And now I already started the traffic light, so let's build and run the traffic light. So that's an application that runs on my local PC now. It would run as well on any microcontroller with or without operating system. Doesn't really matter. It's completely portable. So here you can see now the traffic light is green and red here. So I could press the request button, but nothing happens, of course, because I did not implement it. So let's quit this and have a look at what happened inside my system. So if I want to debug, I have a look at the sequence diagram, and that's exactly what I did here. So I connected and I set the car green ped red, and you even see the button I pressed because it was sent to the controller, but the controller did not react because I did not implement it. But you can see, for example, here the connected state. That's here the state. You have the connect state and the connected state. That's exactly the state here in the state machine. So now I'm going to cheat a little bit now. I'm going to replace this traffic light controller I just implemented. So let's deactivate that one, and that's my cheat code here. And now I have a little bit more implementation. Okay, it's not, I didn't start the layouter here yet, but that's okay. So now that's the complete implementation, a very simple implementation for the traffic light controller. And now let's restart the build and restart the traffic light again. See, it's just a little bit of new code, a model level code, new state machine. So, okay, so now I can push the request button, and you see green light, red light, and so on. So that's exactly what happens here now in the traffic light controller. So I stopped it. Let's have a look what my sequence diagram does now. Here you can see the complete execution. You can also see this on the target then. Now, but we're talking about architecture. Now I've shown you how to implement those components. And now we come to the real power of this approach. So you want to scale up. So I don't want to control one traffic light. I want to control, let's say, 20 traffic lights. So I start 20 traffic lights. And I want to control them, but I already have one traffic light. So now I could, that's the low-level approach. I could add a multiplicity to every one of those components. Would be very easy. It would work out of the box with 20 controllers, 20 interfaces, and 20 sockets without any problem. But we have an architecture. So if I want to reuse something and that's encapsulated, like here in this container, so again in this container we have those 3 elements. So why not creating more of those containers? Well, let's create 20 containers. Now I have 20 traffic light containers. Now let's have a look at what happens when I start the application now. I just created an array of containers, if you want, of traffic light containers, and suddenly I can control 20 traffic lights. They're all completely independent now. If they would be dependent, I could give them a port to synchronize them or to control them centrally, like in an area or in a city where you want a centralized control over those traffic lights, or a green wave control or something like that. So that's how easy it is to create scalable architectures with Room. You really need to. It's really hard to do this with most other methods because it's been designed to design architectures. So now that's the scalability. And now a last aspect I want to show you. I'm going to replace the traffic light just with a test. So now I add, that's a predefined test case. It's empty. So I want to make a software in the loop test. So I add my traffic light controller to the test case, and it only has one interface. I don't even need a TCP/IP. I could test it with TCP/IP, but I want to run a pure software in the loop test. So I hook it up directly to my test case. And now in here I have another language. It's called Cage. It's just another behavioral language which gives me the possibility to design test cases for Room models on any level, on component level, on integration, software integration levels, software in the loop, because it's asynchronous, and also hardware in the loop. And here, for example, I have this test suite that calls the smoke test, which calls a connect step. So let's create the first action. So I have the traffic light interface, and I want to send a connected back, and I wait for a reaction. In this case, I expect a reaction from the traffic light interface. That's the transition I designed before, and I expect a connect. I send a connect. No, I expect a connect. No, let's do it this otherwise. First I connect, and then I expect, for example, in the next step, check initial state. So I check the initial state. So I expect, for example, as a reaction, I expect from the traffic light, just a second, from the traffic light interface, I expect a set car green true. I want to make this false. False. So now that's my test case, and now I just run the system again. And now I start. You see, it's basically, you can do it with tools, you can do it on command line, doesn't really matter. And now the system is running. So it's waiting for a test case. And now I'm going to run the test case here. So that's just a command line interface to run the test cases. And you see, it failed. No, actually, it worked. So let's have a look at what happened now. So now, instead of the graphical user interface, I had this test case attached to the same component. And let's have a look at, of course, I could have a look at the sequence diagram now. This would be the execution of the test case. But much more interesting is to have a look at the traces of the test case. And here, see, I have to connect it and the test passed because I did not call the second step. My bad. So in that case, it would have failed. Okay, so that was the demo. Let's come to the conclusion. So if you want to move on with the software in the loop test to a hardware in the loop, you can use our mini hill. It directly integrates the system under test, the chip, for example, your microcontroller with your software, with all the IOs, and here you can run the room model with the hardware in the loop tests and so on. So you can also use it for non-room models, of course. And in the end, you develop with the same model, you develop the test cases, you let them run on the hardware in the loop test system, and you learn and iterate. Okay, so we have combinatorial test cases in this application as well. So you can really run very high level, very powerful robustness test with the system. Okay, so I hope you enjoyed the webinar. If you have any further questions you did not place in the comments or in the section, don't hesitate to contact me. Or if you have any other questions regarding the tooling or the methods, please contact me, or also Michael Weiss from Hitex. Hitex is our partner in also selling, for example, the mini hill, but the most part what I've shown you is completely open source. Okay, thanks for your attention.